Okay, I wanted to talk just a little bit about section 2.1 now that I've done a couple of simpler examples. So in section 2.1 they introduced the problem. It's a more complicated problem. It fits well in chapter 3, and I think that's part of the reason they do it, but it becomes hard to really go through the coin thing as easily. It's just, as I said, more complicated. So they use this example of promotions, and so there's decision, gender, and again, they're just using for their simplification, I think, male, female. They have a total here. And whoops, promoted, not promoted, and 21, 3, 14, 10, and so that made 24, 24, and 35, and 13, for a total of 48. And now you can go about this the same way, and I want to just talk about that a little bit, but it's much harder, and so that's why we aren't going to try to do simulations to do this. We're going to do the much simpler approach of using mathematical models, in particular the normal distribution, to help us answer questions on something like this. Much easier than trying to put it into Excel or something along those lines. But the idea would be similar. We would, in this case, we would say, okay, we have, our 48 people. So we have those coins. Now 24 of the coins are male, 24 of the coins are female, and each coin, we would say, we would take this and we would have a, I guess if we went with promotion, each coin might have heads at 35 out of 48 chances, not 50-50, like a regular coin. So it's an unbalanced coin, and then tails would be 13 out of 48. And so what we would do is we would line up the 24 males, 24 females, and we would flip a coin for each one of them, and then we would count, and we would, each of our times through this, with those 48 flips of this particular coin, we would then count, well, how many males had a promotion, how many didn't, how many females had a promotion, how many didn't, and we would fill in those 4 boxes, and we would do that a bunch of times, 1,000 times or 10,000 times or something like that. And again, we would ask, well, how likely is it we could have gotten this particular set of data or something more extreme? Well, that's where it gets really hard. I mean, certainly if I had some data where I matched exactly the 21, 3, 14, and 10, I could say, oh yeah, okay, yeah, I matched that exactly, but what's more extreme? And that's where it starts getting hard. Definitely I could say, I think more extreme would be, in this case, if we were looking for essentially equal opportunity for both male and female, then more extreme would probably be either more males getting promoted than 21, or more females getting not promoted than 10, because that would tend to make these numbers even more lopsided. So that's definitely something that's more extreme, but some of those, as you start adding possibilities for decisions, so maybe there's promoted, not promoted, or sort of next on list or something like that, and so it can become very, very complicated as to what's more extreme, and then to keep track of that is just hard, and that's a lot of coin flips. If we needed, say, 10,000 times, but 48 flips each time, that's 480,000 coin flips to try to get a handle on this problem. And that's just, that's too much. So we won't go through and do a simulation for something quite this difficult. But that's the idea. It's you're going through the same sort of thing we did before with the simpler cases. We're just trying to get a handle on how often, if we make this assumption that 35 out of 48 people get promoted, 13 out of 48 do not, and we got that from these columns of promotion and not promotion. If that's what's happening, and we have 24 males, 24 females, then how likely is it we could have seen something as lopsided as this? I mean, because this is very lopsided, right? 21 males promoted to just 3 not promoted, whereas the females, it's 14 and 10. So definitely looks lopsided, but how likely is that? And I believe, let's see, I'm looking at the textbook right now. I don't know. Simulating the study. So they talk about it. Oh, here we go. And somewhere they get an answer down here on page, in the middle of page 65. Okay, what they come up with was you could get this kind of data about 2% of the time. And so if that's the case, then we would reject, and their null hypothesis was that the two rows were the same, or basically the males and females had the same chance. Reject H0, that males and females had same proportion. Okay, because we could only, given the assumption that that was happening, we could only get these data or worse about 2% of the time, according to our text. Okay, so that's what they're doing in 2.1.